You ever just stop and wonder what's really going on inside your computer? I mean, beneath the surface of the apps and Windows. There's one program that's always on, always working, managing absolutely everything. That's your operating system, the OS. It's kind of like the master conductor of this invisible symphony, the true unsung hero of your entire digital life. So let's pull back that curtain and see what it's actually doing.
Here's a question for you. You've got a web browser with a dozen tabs open, maybe a game running, music playing in the background. What's the invisible force field that keeps one buggy app from just bringing the whole system down in a fiery crash? Well, the answer is this really fundamental design principle that's right at the heart of how your computer works.
Okay, so the first thing you need to get is that the OS is a super strict gatekeeper. It puts up this very intentional wall between your applications and the actual physical hardware. Your processor, your memory, your hard drive, and there are some really, really good reasons for that.
This gatekeeper job really boils down to three critical things. First, the OS has to be a fair referee, deciding who gets to use the CPU and memory so one greedy program can't just hog everything. Second, it gives us something called abstraction, which is a fancy way of saying it hides all the messy, complicated details of your hardware from your apps. And third, and this is a huge one for stability, it provides protection by keeping programs isolated from each other. Your word processor has absolutely no business messing with your web browser's memory.
So how does the computer actually enforce all this? I mean, it's not just a polite suggestion. This is a rule that's literally built right into the processor hardware itself. The solution is this brilliant concept called dual mode operation, and it creates two completely separate worlds inside your computer.
And these two worlds, they have names: user mode and kernel mode. To put it simply, pretty much everything you interact with, all your apps, they live in one world, and the all-powerful OS, it lives in the other. So on one side, you have user mode. This is where your apps live. Think of it like a padded, protected sandbox. An app in this mode can't just decide to format your hard drive whenever it wants. But then, there's kernel mode. That's God mode. The OS kernel runs there with total, unrestricted access to absolutely everything. Anytime an app in user mode tries to do something privileged, it trips an alarm, and the system switches into kernel mode, where the OS can step in and handle the request safely. So if an app is stuck in its little sandbox, how does it ask for something important, like saving a file? It can't do it directly. Instead, it has to use a secure official doorway called a system call. It's the only legitimate way for an app to knock on the kernel's door and say, "Hey, I need you to do this potentially dangerous thing for me, please."
Okay, so the OS is this superpowered protector, right? But it's also managing dozens of programs, talking to slow hardware, handling all your mouse clicks, all at the same time. How in the world does it perform this incredible juggling act without slowing down to a crawl? Well, it all comes down to being incredibly efficient.
Let's think about a classic computer problem. Your super-duper fast CPU sends a document to your much slower printer. Now, without a clever trick from the OS, how would the CPU even know when the printer is done? The old-fashioned way? Well, it's just shockingly bad.
It's a method called polling, or sometimes busy waiting, and it means the CPU would literally just sit there, asking the printer over and over, "Are you done yet? How about now? Are you done yet? Done yet?" It would waste millions upon millions of clock cycles doing absolutely nothing useful. It is the technological equivalent of a kid in the back of the car asking, "Are we there yet?"
The beautiful, elegant solution to this is the interrupt. Instead of the CPU constantly nagging the printer, the hardware just taps the CPU on the shoulder when it's done. The CPU can go off and do a million other useful things, and when the printer finally finishes, it sends an interrupt signal. The CPU just pauses what it's doing, deals with the finished print job, and goes right back to its other work. Zero wasted time.
But interrupts only solve one part of the puzzle. What happens if you're copying a huge file? If the CPU has to get involved in moving every single byte of data from the hard drive into memory, it becomes this massive bottleneck. The CPU is forced to be a micromanager, and it can't get any other real work done.
And this is where we see the difference between the old way, which was called programmed I/O, and the modern solution, direct memory access, or DMA. With programmed I/O, the CPU was basically babysitting the entire transfer. With DMA, the CPU delegates the whole job to a specialized controller. It says, "You handle this. Move this giant file from point A to point B, and just send me one single interrupt when the whole thing is done." This completely frees up the CPU to go do something more important.
So all of these efficiency tools, interrupts, DMA, they're what paved the way for the modern computing experience we all take for granted. Early computer systems used something called multi-programming just to keep the CPU busy. They'd only switch jobs when the current one was stuck waiting. But what we have today is true multitasking. It takes that idea and puts it on steroids, using a timer to switch between programs so incredibly fast that it creates this perfect illusion that everything is running at the exact same time.
All right, so we've talked about how the OS manages tasks and processes, but now let's talk about data. The OS also has to manage the huge physical world of storage with all its crazy different speeds and limitations. To manage all this data effectively, the OS has to work with something called the storage hierarchy. Think of it like a ladder. At the very top, you have the CPU's registers. They are insanely fast. It's like notes a chef is reading while they're cooking. As you take a step down the ladder to cache, then main memory, then SSDs, the storage gets way bigger and cheaper, but it also gets much slower. All the way down at the bottom, you have an old-school spinning hard disk, which is like having to drive across town to a giant warehouse to go find your data.
And that speed difference, it is not a small thing. We're talking about a performance gap of over 100,000 times between the fastest part and the slowest part. Managing this insane disparity is one of the operating system's biggest and most important challenges.
For something as slow and mechanical as a traditional hard drive, the OS can't just handle requests in whatever random order they show up. That would be a disaster. Instead, it uses these really clever disk scheduling algorithms to reorder the requests, trying to minimize the physical back and forth movement of the disk's little arm. And that one optimization dramatically boosts performance and makes sure every request eventually gets its turn.
And that kind of brings us full circle back to this core idea. The kernel, which is the heart of the operating system, is truly the one program running at all times, silently, constantly, managing every single one of these complex dances.
You know, when you really think about it, we've gone on quite a journey, from a simple mouse click in an application down into the protected world of the kernel. We've seen how it uses things like interrupts and DMA to tame the hardware and how it manages this vast ladder of physical storage. It really is the master conductor, making sure every single part of this invisible symphony is playing in perfect harmony.
So, the next time you click a button and something just happens instantly, maybe you'll think about that invisible symphony. You'll think about the millions of calculations, decisions, and juggling acts the OS performs every single second just to make it all feel completely effortless for you.